Okay, we're still talking about the end behavior of rational functions in preparation for graphing. In the previous video, we talked about two of the three possible cases, or two of the three rules for the end behavior of a rational function. We talked about when the degree of the numerator is less than the degree of the denominator, that the end behavior is 0. When the degree of the numerator is equal to the degree of the denominator, you just divide the leading coefficients, and that's what the end behavior is. And then now this is the third case. This video is about the third case, is when the degree of the numerator is greater than the degree of the denominator. What do you do in that situation? This has its own video because it's the most complicated of the three. And this I kind of made up this definition here. Like, I tried to use notation for this, but basically you have to divide. You have to do the division that the rational function is suggesting. So divide the numerator by the denominator. And what you'll get is, if it divides evenly, then it's not going to divide evenly, because if it did, you'd have a different function. You'd have a hole in your graph. But what you'll get is a quotient and a remainder, and what you're going to look at is the quotient, and then that quotient determines the end behavior of that polynomial. So let's look at an example of what that means here. All right, we want to know the end behavior of this polynomial. F of x is equal to x squared minus 3x plus 6 divided by x plus 1. So we have to divide x squared minus 3x plus 6 by x plus 1 to determine what the end behavior will be. And we have an easy way to do that with synthetic division. Note that synthetic division will only work when you're dividing by, when your divisor is a linear term or a first degree polynomial. Well, for this case it is, so the value we'll be putting in the little box for synthetic division is -1, and then the coefficients of the dividend are 1, -3, and 6. So we do this synthetic division, and we find that this is 1, this would be -1, this would be -4. Now we don't actually care about anything else. We don't actually care about the remainder. Is -1 times -4 is 5. The remainder ends up being 11, but what I'm interested in is this, which is just x minus 4. And so what this tells me is that the oblique asymptote, or the thing that's going to determine the end behavior of this rational function, is the line y equals x minus 4. Or literally, when I graph this, it is this line, right? I have the graph here, and I have a line. This blue dotted line is at y equals x minus 4. We know that there's a vertical asymptote, right? If we set the denominator equal to 0, we find a vertical asymptote at x equals -1. And so what you get is this, you get this oblique asymptote. Now, in the case when your oblique asymptote is a line, or it's a linear polynomial that you get, it's also called a slant asymptote. But slant asymptote is kind of a narrow word. It doesn't describe all possible oblique asymptotes. In the next example, I have a not, it's not at all a line, okay? And so now the answer to this question, like if you look at the notation I wrote on the previous slide, the limit as x approaches positive or negative infinity of f of x, it would suggest that it'd be x minus 4. And this is kind of right. However, x minus 4 is, we can know the limit of x minus 4. This is just an odd degree polynomial with a positive leading coefficient. And so the end behavior of this is two different statements. The limit, so this is okay, this is acceptable. Some teachers will let you do that. But the real answer to this is the limit as x approaches positive infinity of f of x is going to be infinity, right? As I'm plugging in really big positive x values, I'm getting really big positive y values out. And also, so two statements here, the limit as x approaches negative infinity of f of x, right? If we were going the other way, that would be negative infinity. So that's what an oblique asymptote is. It's not super difficult, but conceptually it's kind of a strange thing. Let's look at a way stranger example. In the previous problem, the degree of the numerator was just 1 greater than the degree of the denominator. We had a second degree polynomial divided by a first degree polynomial, so the degree of the quotient was 1. And so what we ended up with was a line. Our oblique asymptote took the form of a line, and we called it a slant asymptote. Well, in this problem here, the degree of the numerator is 2 greater than the degree of the denominator. We have a cubic term, a third degree polynomial, divided by a linear factor. And so what we'll get is our quotient, the degree of our quotient is going to be 2 degree, which means our oblique asymptote is going to be a quadratic, which is super weird. It's going to be a parabola. But we can still do synthetic division here. So we'll take x cubed minus x squared minus 6x plus 6, and we're dividing it by x plus 1. So synthetic division, we've got 1 times -1 is -2. This would be 2, so we have -4, and then we have -1 times -4 is +4. We have 10 here. We don't really care about that 10, because what this tells us is that our quotient of this division problem here, our oblique asymptote, is going to be x squared minus 2x minus 4, which is a parabola. And we could go a step further here. If we wanted to actually plot this, right, we could plot this parabola, but we'd have to complete the square. X squared minus 2x minus 4. We'd have to add 1 here to make that a perfect square trinomial, and subtract 1. So we would have here is a y equals x minus 1 quantity squared minus 4. So this is just a pretty standard, minus 5. This would be a pretty standard parabola with its vertex at 1, -5. And let's look what this looks like. This function is weird. Okay, notice first of all that the scale of this is off, right? I have set it so that each line on the x direction is 1 and each line in the y direction is 2. Okay, so we have that parabola right there. It's our vertex is at the 1, -5. And notice how this function works. Now this is all stuff we could determine. We could determine where the x-intercept is by setting the y equal to 0 and solving for x. We could determine, and this would be very difficult for this one because it doesn't have a clear factor. We'd have to use the rational zeros theorem. Then we could easily find where the y-intercept is. I think the y-intercept looks like it's going to be 6. Because we'd have 6 divided by 1, right? Because this would be 0, 0, 0, 0, and we'd have 6 divided by 1. So those would be easy to find. And then we have the vertical asymptote at x equals -1 still. And then we have this weird parabola. So the only thing that could happen was if we had a y-intercept right there and an x-intercept right there, this data would have to do this, okay? And it would have to then also, because we don't have any more x-intercepts, it couldn't be over here, right? It would have to be up in here because there's no other y-intercepts either. And so by logic, we can figure out how to graph these things. But this one here is insane. This one would be really difficult to graph. But anyway, that is how oblique asymptotes work. Now, the last piece of the puzzle here is just to do the further analysis on these functions. So when is it less than 0? When is it greater than 0? Or when is it positive? When is it negative? And when is it increasing? And when is it decreasing? Now, the one difficult part of that is determining where are these little values? Where are these different values where we have what are known as turning points between essentially when the slope of the line tangent to these curves, when is it 0? That's what a turning point is when we can determine when it changes from increasing to decreasing. And that's the last step. And that we've done that before with polynomials, so we're going to put it all together in the next video. One last thing on this, actually. Forgot to mention what the actual end behavior would be. So we determined that the limit as x approaches positive or negative infinity for this function f of x was that parabola, right? We said it was x minus 1 quantity squared minus 5. Now of course the end behavior is determined by the end behavior of this parabola. It's an even degree polynomial with a positive leading coefficient, so both ends of this thing go up. And so for this one, you can actually write it in one statement. The limit as x approaches either positive or negative infinity of f of x is going to be infinity. Because look, as we go farther that way, we're going to go up farther that way. As we go farther right, big positive x values, big positive y values. Big negative x values, big positive y values. Positive y values, positive or negative x values. All right, next video puts everything together.